Welcome to today's deep dive. Today we're basically handing you the keys to a quantum vault.
Yeah, a very, very small vault.
Right. We are taking just a handful of, seemingly inert uranium dust, and we're tracing its journey from a single, microscopic collision all the way to the 240,000 volts that are currently lighting up your neighborhood.
Quite the journey, yeah.
It really is. So we're calculating the precise energy unleashed by exactly 1 mole of uranium-235, and then we're pulling that abstract physics math down to Earth by converting it into everyday kilowatt hours so you can actually grasp it.
Because it is entirely one thing to just, acknowledge that nuclear energy is powerful. I mean, everybody knows that.
Yeah.
There's another thing entirely to physically comprehend the staggering scale of that power.
Absolutely.
The goal here is to really make you feel the weight of these numbers, bridging that massive gap between a tiny fraction of a joule and the sheer relentless force required to power a whole city block.
All right, let's unpack this, because we really have to start at the absolute bottom. Before we scale up to massive quantities like a whole mole, we have to understand the microscopic trigger, the spark, basically.
The initial event.
Right, and it relies entirely on velocity. A slow-moving neutron, it just bounces off a uranium-235 nucleus. Nothing happens. It takes a high-speed neutron striking that nucleus with immense force to actually shatter it.
Yeah, that high-speed impact is completely non-negotiable.
Yeah.
I mean, the strong nuclear force is literally the strongest force in the universe.
Right.
And it is holding that nucleus together tightly. So when a fast-moving neutron finally overcomes that barrier, it destabilizes the nucleus. And the resulting physical split unleashes a tremendous burst of thermal energy alongside several rogue neutrons that fly off to continue the chain reaction.
So imagine a giant overinflated water balloon, right? It's already wobbling. It's incredibly unstable.
That's a good way to picture the U-235 nucleus, actually.
Yeah, and the high-speed neutron is like a dart hitting it. But the balloon doesn't just pop and make a mess. It violently splits into 2 smaller balloons, throws off this blinding hit, and then shoots out 3 more darts in the process.
Which then go on to hit other wobbling balloons.
Exactly. And the energy released from just that first initial break, that single atomic fission, is 200 megaelectron volts. Or 200, that's the baseline measurement in particle physics for this.
Right. And what's fascinating here is the sheer contrast between the catastrophic nature of that event at the atomic level and its actual energetic value in our macro world.
Because it's tiny, right?
Oh, it's microscopic.
Right.
When we take that 200 MeV and we look at it through the lens of joules, which is, our standard everyday unit of energy, the math comes out to approximately 3.204 times 10 to the negative 11th joules.
Wow.
Yeah. You would have to write 10 zeros after the decimal point before you even reach the 3.
That is hard to even visualize.
It really is. I mean, a standard 100-watt light bulb burns through 100 joules every single second. So on its own, this violent microscopic event registers as, well, almost nothing.
Yeah, so if it were just one atom splitting in isolation, it wouldn't even warrant a footnote. The true terrifying majesty of nuclear physics doesn't come from the single atom. It comes from the swarm.
The swarm, exactly.
When we scale up from a single atom to a full mole, which is Avogadro's number, 6.022 times 10 to the 23rd atoms, the math just gets entirely staggering.
Just picture 6.02 with 23 zeros trailing behind it.
It's absurd.
Right. But in terms of physical volume, 1 mole of uranium-235 is remarkably small. I mean, we were talking about a handful of dust. You could literally close your fist around it.
A single handful.
Yeah. Yet the latent potential inside that tiny confined space is, well, it's what reshaped human history.
So let's do the actual calculation here for you listening. We take our tiny energy output from one single atom, that 3.204 times 10 to the negative 11th joules, and we multiply it by the swarm, Avogadro's number. 6.022 times 10 to the 23rd atoms. The output of that equation is a massive 19.3 trillion joules.
Trillion.
Trillion, with a T coming from a handful of material.
If we connect this to the bigger picture, so humanity's entire technological ceiling is basically dictated by energy density. Our ability to progress relies on packing more power into smaller, more manageable spaces.
Which makes sense.
Yeah. And generating 19.3 trillion joules used to require literal mountains of coal or, massive sprawling reservoirs of water. Now it fits in a coffee cup.
To really ground that 19.3 trillion joules, let's bring it back to your monthly electricity bill so you can actually feel what that number means.
Good idea.
Right, because nobody really uses joules to pay for things. When you convert those joules into standard kilowatt hours, which is a watt hour is just 1 watt of power sustained for 1 hour, so standard kilowatt hour, the math translates to an astonishing 5.36 million kilowatt hours of usable energy.
That is just a huge leap. And to put 5.36 million kilowatt-hours in perspective, the sources we analyzed highlight that this specific amount of energy could easily power a typical home for over 500 years.
Wait, really? 500 years?
5 centuries, running a modern household's air conditioning, heating, refrigeration, your electronics, all of it, sustained by a clump of uranium dust.
Okay, so we have 5.36 million kilowatt hours of potential energy sitting in our hands. But right now, it's just, well, it's uncontrollable, dangerous heat.
Yeah, very dangerous.
You can't just, plug a USB cable into a glowing rock to charge your phone. To actually capture that heat and send it to the grid, engineers have to build this staggering mechanical labyrinth.
And that labyrinth begins long before the uranium ever even sees the inside of a reactor core.
Right, the enrichment.
Exactly.
Yeah.
Because raw uranium ore straight out of the ground doesn't have the right concentration of the U-235 isotope to actually sustain that chain reaction.
So how do they boost it?
Well, the sources emphasize the role of a naturally occurring uranium-bearing mineral called graphite.
Oh.
Yeah. This graphite is essential for the initial enrichment stage. It acts as a booster, essentially, concentrating the fissile U-235 just before the fuel goes through the gaseous diffusion process.
And gaseous diffusion is an intensely demanding process. I mean, they're forcing uranium gas through these microscopic porous barriers over and over.
Because the U-235 isotope is just fractionally lighter than the other isotopes.
Right, so it squeezes through those barriers just a tiny bit faster. And you repeat that process until the fuel is enriched enough to maintain the reaction. Once that enriched fuel finally goes into the core, the mechanical loop takes over.
The primary circuit.
Exactly. Inside a pressurized water reactor, or a PWR, the constant fission intensely heats the fuel rods, which in turn warms the surrounding water in the primary circuit loop to, well over 300 degrees Celsius.
And the physics of that primary circuit are totally crucial. The water is heated way beyond its normal boiling point, but it is kept under immense pressure.
So it doesn't boil.
Right? That high pressure physically prevents the water from turning into steam. It remains a liquid, which is critical because the reactor relies on the density of liquid water to moderate the neutrons.
Okay.
So that superheated, highly pressurized liquid water then rushes into a heat exchanger, which is known as a steam generator.
And inside that generator, the superheated primary water transfers its immense thermal energy to a completely separate body of water, which is the secondary circuit.
And they never mix.
Yeah, that's key. The primary radioactive water never actually touches the secondary water. It just acts as a thermodynamic bridge. And because the secondary circuit operates at a lower pressure, the transferred heat causes it to boil instantly, flashing into highly pressurized steam.
And that violent blast of expanding steam is funneled straight through pipes to strike massive high and low pressure turbines.
Just huge steel blades.
Yeah. The steam physically forces these massive steel blades to spin rapidly on their shafts. The spinning shafts are coupled directly to a generator, which converts the rotational kinetic energy into an electrical current,
Ultimately sending a whopping 240,000 volts out to the power grid.
Afterward, the spent steam hits a condenser, turns back into water, and the excess waste heat plumes out of those massive, iconic cooling towers that, everybody pictures when they think of nuclear plants.
Pressurized water reactors are definitely the standard, but the sources also detail boiling water reactors, or BWRs, which kind of simplify the loop by letting the water boil directly inside the core.
Which has its own pros and cons.
Yeah, for sure.
Yeah.
But here's where it gets really interesting. CAN-BU reactors. They bypass the standard water entirely and use a totally unique moderator called liquid fluorescent oxide, or LFO.
Right. And we should clarify, the role of a moderator is to slow down the rogue neutrons so they are more likely to trigger another fission event.
It's like throwing a ping pong ball at a bowling ball.
That's a great analogy. The ping pong ball bounces off the heavier atoms in the moderator. It loses kinetic energy with every bounce, slowing down without actually being absorbed.
And the LFO moderator is so remarkably efficient at stripping kinetic energy without absorbing neutrons that CANDU reactors don't even need enriched fuel.
Right, they can run on natural, unenriched uranium, entirely skipping that massive graphite enrichment phase we discussed earlier.
So what does this all mean when you strip away the billions of dollars of infrastructure, the advanced mathematics, and the intricate quantum physics? The irony is glaring.
How so?
We are splitting the foundational building blocks of matter. We are calculating 19.3 trillion joules of thermal output, and we are using all of this futuristic space-age science just to boil water and spin a giant metal wheel.
When you put it like that, yeah.
It is essentially the world's most complicated, dangerous steam engine.
We are leveraging the fundamental forces of the universe to make a glorified tea kettle whistle loud enough to spin a fan.
Exactly.
But the danger, of course, lies in the fact that spinning that massive wheel requires a continuous, completely unyielding flow of extreme heat. Maintaining that heat without letting it spiral out of control is the ultimate engineering challenge.
Right, because they have to manage the neutron flux, which is the total stream of neutrons flowing through the core at any given millisecond.
It's a delicate balance.
A high flux is a raging flood. Way too many neutrons are initiating fission, escalating the risk of a catastrophic meltdown. A low flux is a dry stream. The fission slows down, the heat drops, and your 240,000 volts flatline.
So operators use control rods, usually made of neutron-absorbing materials like boron or cadmium.
They act as the brakes.
Right, they physically drop into the core to soak up neutrons.
Yeah.
The control rods are the mechanical brakes, but the thermodynamic environment itself actually plays a massive role in regulating the flux.
The water temperature.
Yeah. The temperature of the water acting as the moderator is deeply intertwined with the rate of fission. The mechanics governing this relationship are highly complex.
Actually, I have to jump in here because the sources present what looks like a glaring contradiction regarding those mechanics, and I feel like we need to untangle it.
Okay, let's hear it.
So the text explicitly claims that if you want to decrease the probability of fission, you raise the water temperature.
Right.
It states that increasing the temperature lowers the mean fluoride concentration, making the water slower, and reducing the average number of neutrons available to accelerate. So, hot water equals less fission.
Yes, that describes the change in the moderator's density.
But literally a few paragraphs later, the same source material introduces the neutron drift model, and this model argues the exact opposite.
Ah, I see where you're going with this.
Yeah. It states that higher temperatures actively increase random neutron drift, causing neutrons to move more erratically, giving them a higher probability of striking the fuel. The text explicitly says, and I quote, "Higher temperatures mean increasing the number of neutrons available to initiate fission."
Yes, it does say that.
How can a higher temperature decrease fission probability by lowering fluoride concentration, but simultaneously increase fission probability by increasing neutron drift? Which is it?
This raises an important question about the reality of reactor dynamics. You haven't found a typo in the physics. You have isolated the fundamental tension that reactor operators manage every single day.
So they are both happening.
Both of those seemingly contradictory phenomena are occurring simultaneously inside the core.
Okay, walk us through how they coexist, because it hurts my brain a little.
It's a lot, I know.
Yeah.
So the water is acting as both the coolant and the moderator. When the temperature of the water rises, thermal expansion occurs. The water physically becomes less dense.
Right, water expands when it gets hot.
Exactly. That physical drop in density alters the mean fluoride concentration, meaning there are fewer moderator atoms in a given volume to bounce against the neutrons.
Okay.
The neutrons don't slow down efficiently, and fast neutrons are less likely to cause fission. This acts as a negative feedback loop. If the core gets too hot, the physics naturally attempt to dampen the reaction rate.
Okay, so the expanding water makes it a less effective moderator, inherently pulling the brakes on the fission process.
Right. But simultaneously, we have to look at the kinetic energy of the particles themselves, which is the neutron drift model.
The other side of the coin.
Exactly. In that hotter, highly energized environment, the neutrons are bouncing around with intense, erratic movement. This random drift increases the sheer volume of chaotic interactions, providing more statistical opportunities for a neutron to accidentally strike a uranium-235 nucleus at the correct angle.
Oh, wow. So the physical environment is expanding and trying to starve the reaction, but the individual neutrons are getting hyperactive and trying to accelerate it.
Yes. It is a microscopic tug-of-war happening millions of times a second. The density of the moderator is pulling one direction, and the neutron drift is pulling the other.
That is wild.
And the operators sitting in the control room are constantly monitoring these deeply opposing interactions. They are making, millimeter adjustments to the boron and cadmium control rods to ensure that this tug-of-war stays in a perfect continuous tie.
Because if either side wins,
If either side gains a meaningful advantage, the entire system either powers down completely or risks melting right through the containment vessel.
that level of precision is terrifying. You are essentially trying to balance a needle on its point during an earthquake, all while extracting 5.36 million kilowatt hours of energy from the friction.
It is an incredible feat of engineering.
It really is. But that extraction comes with a deeply permanent cost. I mean, we've calculated the massive energy of a mole, we've converted it to usable voltage, and we've balanced the conflicting physics of the neutron flux. However, shattering 6.022 times 10 to the 23rd atoms inherently leaves behind a massive amount of debris.
Yeah, the waste. The fission process fundamentally transforms the uranium. When you shatter the nucleus, the resulting pieces are entirely different elements, known as daughter products.
And they aren't safe?
Not at all. The sources highlight that the most common products from uranium-235 fission are various isotopes of lead. Lead-206 is the most abundant, found alongside lead-207 and lead-216.
But the lead isotopes are just part of the problem. The core also breeds highly radioactive, violently unstable isotopes like barium-137, strontium-90, and thorium-90.
Right.
These aren't just warm rocks. They are chemically chaotic elements desperately trying to find stability by ejecting dangerous alpha, beta, and gamma radiation.
And strontium-90 is particularly hazardous. Because of its specific decay mechanics, it requires incredibly secure, robust, long-term storage solutions.
Because they stay dangerous for a very long time.
Exactly. The decay process of these heavy, unstable isotopes doesn't happen overnight. They will continue to eject harmful radiation for generations, presenting a massive waste management challenge.
A huge trade-off.
It is. We have engineered the ability to master microscopic collisions for today's power grid, but we are leaving behind a volatile legacy that future generations are obligated to manage.
It is the ultimate double-edged sword. We gain 500 years of electricity for a home out of a single handful of material, but we generate toxic byproducts that have to be guarded and contained for timelines that outlast human empires.
Which leaves us with a profound reality to consider.
Yeah.
We've spent this deep dive outlining the immense labyrinthian effort required to safely extract energy from just one specific type of atom. We are balancing contradictory physics, enriching graphite, and managing microscopic explosions just to harvest the heat that spills out when an atom breaks.
Right.
But if human ingenuity can manipulate the strong nuclear force just enough to fracture a nucleus, what happens when we look beyond simply breaking things?
Oh, that's an interesting thought.
What happens when our understanding of the atomic scale evolves to the point where we can manipulate those fundamental, invisible forces directly, potentially rendering the messy, radioactive steam engines of fission entirely obsolete?
When you really stop looking at the universe as like a collection of inert dust just waiting to be broken, you realize the greatest power might not come from shattering the vault, but from finally learning how to rewrite the code of the vault itself.